Hello everyone, I am Dr. Ranjan Dutta from Haldia Institute of Technology, and in this video lecture, I will discuss synthesis of some common polymer which are used in our daily life. Now, as you can see, polymers are everywhere. And so in the introduction part, so I have shared some examples of natural polymer and some synthetic polymer. For instance, DNA, RNA, and this natural rubber are actually natural polymer because they can be obtained from natural resources. Whereas plastic, Teflon, they are synthetic polymer. They can be prepared in lab. And as per some recent statistics, polymers are predominantly used in packaging industry, also in automotive industry and construction industry. Means polymer actually are indispensable in our daily life. And here are some material which are made from polymer like plastic bottle, pipe, chair, etc. Now, in this video lecture, mainly we will discuss synthesis of some common polymer. Those are HDP, means high density polyethylene, low density polyethylene, and nylon. So they can be prepared by either addition polymerization or condensation polymerization. This HDPE and LDPE can be prepared by addition polymerization, whereas nylon are prepared by condensation polymerization. Now, high density polyethylene, which is in short known as HDPE, is defined by the density always greater than 0.941 gram per centimeter cube. And it features low degree of branching and stronger intermolecular forces because it contains lower degree of branching, so intermolecular forces will be more. And it is designated by this symbol, this triangular loop. Inside we have this number 2. So it means high density polyethylene can be easily recycled. And here are some material which are made from high density polyethylene. Now, high density polyethylene are mainly prepared by this famous catalyst, Ziegler-Natta catalyst. Now, so it was so important that in the year 1963, German scientist Carl Ziegler and Giulio Natta for their discovery in the field of chemistry and technology of high polymer. Now, Ziegler-Natta catalyst is a combination of titanium tetrachloride and triethyl aluminum. So in the first step, so during activation of catalyst, ethyl group from triethyl aluminum is transferred to titanium tetrachloride. And in the crystal structure of titanium tetrachloride, we have one titanium center and 6 chlorine atoms. So when triethyl aluminum comes to titanium tetrachloride, one ethyl group is transferred to the titanium center, and during the process, one chloride is kicked out. And finally, we have a titanium center which has one empty orbital. Now, the mechanism behind this binding of the initiation step, where the incoming alkene forms a complex with the titanium metal, and specifically, titanium contains an empty dxy orbital, as you can see from here, and a filled dx square minus y square orbital. On the other hand, our alkene, which contains a double bond, have a filled pi bonding orbital and empty pi anti-bonding orbital. Now, when alkenes comes closer to titanium, there will be sharing of electron between the pi bonding orbital and the empty dxy orbital of titanium. So, at the same time, there will be sharing of electron between empty pi antibonding and the filled dx square minus y square orbital. So by this way, this metal alkene bond is formed. Now, so after that, there will be there will be reshuffling of electron, and there will be shifting of electron, in the complex. And so during the shifting, so we will have the final complex, this one, and there still will be one empty orbital which can accommodate one more alkene. So this is the chain initiation step. So the second step will be chain propagation. So in the chain propagation step, when other alkene comes in, the process starts over and giving linear polyalkene, which is actually polymer. As you can see in the propagation step, the second alkene is coming and the process is repeating. So we are getting a linear olefin. The final step of any polymerization process is chain termination step. So here we will get the dead polymer, means which is the desired product. So there are various pathways for formation of the final product. One is beta elimination, which is shown in the first pathway. By this way, we will get the desired or the dead polymer. Now, so as I told earlier, Ziegler-Natta catalyst is used for preparation of high density polyethylene. So the main advantages of this particular catalyst is that it will facilitate polymerization of alpha olefins such as polyethylene, polypropylene, polybutene. One. And one more important thing is that stereochemistry of polymer can be controlled by using Ziegler-Natta catalyst. Either we will get isotactic polymer, where the orientation of the alkyl group will be in the one direction, or we will get syndiotactic. There will be alternative orientation of the pendant alkyl group. And we can control also the molecular weight of the polymer using Ziegler-Natta catalyst. Now, it is so widely used that as per information from 2023, the Ziegler-Natta catalyst market value is around $4.34 billion. Now, there are some also limitation of this catalyst. One is that vinyl chloride cannot be polymerized by Ziegler-Natta catalyst. At the same time, acrylate polymer cannot be produced using Ziegler-Natta catalyst. So for the industrial preparation of polyethylene, this diagram is shown here to show the industrial production of polyethylene. As you can see, so in the beginning, ethylene is inserted inside the chamber under pressure, where it polymerizes under the influence of Ziegler-Natta catalyst. So after the reaction, the produced polyethylene, unreacted ethylene, solvent, catalyst, they are passed to the reactor, and the unreacted polyethylene is separated and returned to the reactor, where the catalyst is neutralized and filtered out. Finally, a dryer dry the wet polyethylene, and we get the polyethylene in the form of powder. So this is the synthetic part of high density polyethylene. Now we will move to our second polymer, which is low density polyethylene. Now, low density polyethylene is defined by its density in between 0.91 to 0.94 gram per centimeter cube, and it features high degree of branching. That's why the intermolecular process is weak in this particular class of polyethylene. And this is denoted by this triangular loop. Inside we have this 4 number, means it cannot be recycled easily. Still, we have various application of low density polyethylene, as you can see from here, in pipe, films, plastic bag, plastic bottle, etc. Now, for the preparation of low density polyethylene, free radical polymerization method is used. Now, in any free radical polymerization method, we need one initiator. Mainly benzoyl peroxide or some azo compound are used as initiator. As you can see, the first one is tertiary butyl peroxide, which is acts as initiator. We have benzoyl peroxide, and we have azo this isobutyronitride, which also acts as an initiator. For instance, you take the example of benzoyl peroxide. Under heating condition, it produces this phenyl radical, which is actually the initiator. So in the initiation step, so we provided here two examples. One is styrene to polystyrene and ethylene to polyethylene. So our initiator react with the monomer to produce this active monomer. Means you can see phenyl group is added and we have a radical here. Here you can see phenyl group is inserted. We have a radical at the carbon. So this is called the active monomer. So this is the chain initiation step. So in the chain propagation step, other monomer will come, will react with the active monomer, and the polymer chain will simply propagate. Okay, and the radical will be in the polymer chain. Okay, means the incoming alkene react with the active monomer to produce the polymeric chain, which still contains the radical. So this is the example for styrene, and this is the example for ethylene. This is the chain termination step of free radical mechanism. So chain termination can be done by two different methods. One is combination, one by disproportionation. In the combination step, two radical can be combined to form the polymer chain. Whereas in disproportionation step, one of the polymer chain will be oxidized, means this double bonded one, and another polymer chain will be oxidized to form this one. So simultaneously, this both oxidation and reduction is occurring. That's why this is a disproportionation step for the formation of the final polymer. Now, two other very important polymer which can be made by free radical mechanism are Teflon and PVC. Teflon is a synthetic polymer made by addition polymerization from the monomer tetrafluoroethylene. So it's a fully fluorinated polymer, and you can see from the left side. And PVC is a synthetic polymer made from vinyl chloride by addition polymerization. Here are some fun facts regarding Teflon. First of all, Teflon is hydrophobic and water resistant, and it is widely used in, you can see, coating of non-stick pen and some other cookware. Actually, it was accidentally discovered during a process. And importantly, it is produced by free radical polymerization of tetrafluoroethylene. Now, PVC, as I told you, is also a polymer which produced by addition polymerization via free radical mechanism. It was also discovered accidentally by the German scientist Eugen Baumann when he was working with vinyl chloride. Now, as per information, PVC is world's third most widely produced synthetic polymer, and it is, as all of us aware about this fact that PVC is used for construction of pipes, doors, and windows. And importantly, so it is prepared from vinyl chloride by free radical mechanism. And importantly, PVC is recyclable. Because PVC can be reformed at extremely high temperature, it opens up a whole new world of recycling and reuse possibilities. Recycled PVC is frequently broken down into small pieces and refined to pure white PVC after impurities are removed. So these are four different types of polymer we discussed. First one was HDP, then LDP, then Teflon, and PVC. And all of them are prepared by addition polymerization method. Now, nylon 6 and nylon 66. So they are polyamide polymer because it contains amide functionality, which is NaCO. And, and as you can see, they are prepared by condensation polymerization method. And they are widely used for textile and plastic industry. So first we will discuss nylon 6, which is prepared from only one monomer. Means here the monomer used here is caprolactam. Ring opening polymerization of the cyclic amide produce nylon 6. Okay. Whereas nylon 66 is made from two different monomer. So we can tell this one is a copolymer. The two monomer used here is adipic acid and hexamethylene diamine. Condensation of these two polymer upon removal of water produces the nylon 66. So in summary, so in this video lecture, we discussed synthesis of some commonly used polymer such as high density polyethylene, low density polyethylene, PVC, Teflon, nylon 66, and nylon 6. Some of them are prepared by addition polymerization, some of them are prepared by condensation polymerization. And all of them have wide application in industry and in our daily life. Thank you.